Hi everyone, so today's lesson is about the number e and compounding interest continuously. So the number e is an irrational number, which we've talked about this year, and an irrational number, remember, is a non-terminating, non-repeating decimal. And the number e is approximately 2.718. Now we're going to get into a discussion about the number e, but we also call it the natural number or the Euler number or the natural base number. And it actually does occur naturally in any situation where a quantity of some sort increases at a rate proportional to its value. So the number E comes up when, like, we talk about a bank account producing interest, or maybe a population increasing as its members, the people in the population, reproduce. So to put it another way, the number E is related to how much money you'll earn under compound interest, that it's compounded continuously rather than just simple interest. So, and we're going to talk about it more in class. But for now, let's remember that the number e is approximately 2.718. You can use properties of exponents to simplify with e. For example, e cubed times e to the fourth, power times the power, add them high. So 3 plus 4 would give me e to the 7 power. Same thing with the division of exponents. 5 goes into 10 twice, and you can bring the smaller to the larger and subtract. So this would be 2 to the e, or 2e, sorry. And the last one, making sure that there's a 2 on the outside of the parentheses, so we want to square everything within. So 3 has to be squared, which is 9. And then negative 4x times, or squared, is e to the negative 8x. All right, we can also evaluate e on our calculator. So if you grab your calculator, I will grab my calculator right here. The number e, you can find it if you press the second button and you go down to where it says ln, and you'll see it right above it, it says e to the x. Okay, so now we can evaluate e squared by just typing in a square. So it's going to take 2.718 and then square it. So 7.38. You can also do e to the, so negative 0.06. Oops, and I forgot to make it negative. Now remember, when we put in a negative exponent in here, we want to use this negative button right here, 0.06. And it gives us 0.9417. So you can find e on your calculator. Again, it's right above the ln feature. All right, let's put that aside for a second. All right, the graph, graphing e. Okay, and we've been talking a lot about exponential growth and decay, and e grows and decays. It is an exponential function. And for me, I want us to really just understand that we know growth looks something like this. Now, we can plot some points on it. Remember, we can always find our y-intercept. If we do e to the 0, we're going to get the number 1. So we know that the point 0, 1 is always going to be on the graph of e. And you could plot some other points. You could do e to the negative 1 or e to the 1 and get 2.718. But the graph is going to grow just like our exponential graph. Something like that. It does have an asymptote, similar to just the regular exponential growth, y equals ab to the x at y equals 0. Its domain, again, negative infinity to infinity, all real numbers, and the range in this case would be y is greater than 0. All right, so now graphing e to the negative x, remember, that means 1 all over e to the x, right? And it's exponential decay in this case. So let's actually plot some points. So I can still do e to the 0. Like if I had done e to the negative x and I did e to the 0, it would give me 1. And we know that it's going to decay like this. Something like that. It does still have that asymptote at y equals 0. And my domain, again, is still negative infinity to infinity, and the range is y is greater than 0. Now, I'm not going to go into detail on shifting these graphs, but I just kind of want you to know some basics about the graph. If I have a 2 up here in front of the function, remember that's going to vertically stretch it, so it's going to get it closer to the y-axis. If I look at y equals e to the, and let's just change that to just e to the x. Let's change this one to y equals e to the x plus 1. We know that our whole graph is being shifted up 1, okay? So that means that my y-intercept, if I do my y-intercept, is going to become 2, so 0, 2. And my asymptote is going to shift from y equals 0 to y equals 1. So something like that. But again, it's general growth, just like that. Okay, so let's just look at these and see if we can determine the horizontal asymptote of the function. So similar to what we were doing, remember the horizontal asymptote comes from the value being added or subtracted on the outside of the function. So in this case, my horizontal asymptote would be y equals 2. In this one, my horizontal asymptote, this graph is being shifted down 3, so y equals negative 3. And in this case, my horizontal asymptote is being shifted down 1, so from y equals 0 to y equals negative 1, those horizontal line equations. But we're not going to do too much graphing with e. I just want you to get an idea of how it relates to the growth function. All right, but what we are going to be talking about is a great use of e in a real-life example. So anytime we're looking at a bank or a savings account that is compounded continuously, so not annually like the equations we had done earlier, we can use the formula P times E raised to the RT, PE to the RT. And I'm going to give you a little song for that one so that we remember it. So P represents principal. So the amount that we invested, our original amount, our initial amount. E is just going to be its number itself. So we're going to leave E as its own letter or own number. And then R is our rate. Remember, we always express it as a decimal. And when we change a percent to a decimal, we move 2 places, 2 decimal places left. And T is time. PE to the RT, PE to the RT. All right, so Stephen invests $2,000 in a savings account paying 6% annual interest. Find the balance after 5 years. Okay, if it's compounded continuously. So as soon as I see compounded continuously, I know that I can use the PERT formula, PE to the RT. The PERT formula is what we call it. All right, so my initial amount was $2,000. Okay, and we'll leave it as A at T. $2,000 times E. My annual rate is 6, so I'm going to turn that into a decimal, so 0.06. Remember, we move it 2 decimal places, so 0.06. And the time is 5 years. All right, now when we're putting this into our calculator, we are going to want to be really careful. So let me clear. All right, so we're going to do 2,000. Now, each calculator, remember, is slightly different. And then I'm going to put in the E. So second E. Now here, we've got to make sure that 0.06 and the 5 stay up in the exponent. So we've got to make sure that if we need to on the older ones, we put our parentheses around it. All right, so I'm going to put in 0.06 times 5. Now, I have the newer calculator, but some of the older ones, you'd want to put that whole value in parentheses. And so he's going to have approximately 2,600, and actually let's round to the nearest, so $2,700 after 5 years if it's compounded continuously. That's going to be more than if it's compounded annually. All right, let's try another one. We have 2 investment plans, so we're going to compare now. 2 investment plans, each have annual interest rates of 3.275%. One plan compounds, we're going to change the monthly to yearly, while the other compounds continuously. So yearly means annually. If $5,000 is invested in each plan for a period of 10 years, how much interest will accrue to the plan that compounds continuously. All right, so let's do both. Let's see what we're going to have after 10 years in compounding annually. So that's our normal formula, a sub 0 times 1 plus r to the t, okay? All right, so our annual amount, our initial amount was $5,000, and our annual rate is 3.275%. So that as a decimal, that's 0.03275, okay? So 1 plus that's going to give me 1.03275 to the 10 years. Okay, so we'll calculate that now. We grab the calculator, and we're going to do, I'm going to actually do that one. 1.03275 raised to the 10, and I know I'm doing it separately, but times the 5,000, and that's going to give me, okay, at the end of the, after 10 years, we're going to have in the account $6,901.16. Okay? So we've made $1,901.16 in interest. All right, let's look at compounding continuously. So I see that continuously, that means PE to the RT. So my principal was 5,000. My rate was 0.03275 times 10. Okay, so I'm going to go to my calculator. I'm going to plug that in. So clear. I'm going to do 5,000 second E, and I'm going to do 0.03275 times 10, and I get $6,937.48. So $6,937.48. So I made $1937.48. Now that might not seem like that much, $36 and something. But what if the value that I invested was much more? So compounding continuously is going to give you more money instead of annually. That means that every single millisecond it's compounding that money that you're making in interest. So it's just a nice way for you to think about your money, like what you're going to do with your money. Are you going to want to put it in a bank account that compounds annually or compounds continuously? All right, so hopefully you get the idea of using the compound continuously formula, PE to the RT. In class tomorrow, you guys are going to be practicing on the additional questions in your packet. Hope you guys have a great day. Bye.